Hi, my name is Marvin, and I will introduce our paper, Robot Perception Enables Complex Navigation Behavior via Self-Supervised Learning. So we are interested in robot navigation tasks at city scale in the real world. Here we show a recent work on this problem, where a deep reinforcement learning agent is successfully trained for while driving navigation across multiple cities. However, this method has a number of limitations, such as heavily relying on the quality of GPS data, which is used for image labeling in a fully supervised learning manner. Moreover, generalization capabilities to drastic environmental changes are not reported. Now, let's see why addressing these shortcomings are important for enabling long-term navigation autonomy. Here, for example, we have two different large-scale driving datasets recorded across multiple month-spaced periods. The Northern dataset on the left provides 4 long image sequences of a train journey, and its raw GPS data seems to be consistently accurate across each season. On the other hand, the two traversals of the Oxford dataset contains poor and no GPS data at all, which might be not reliable for directly using along supervised learning methods. For those reasons, we believe that self-supervised learning might be really helpful for solving these perception problems. Self-supervision have shown promising results in a range of visuomotor tasks, including robotic manipulation. These methods have proven to jointly learn both motion and visual perception skills without human annotation, while generalizing to new objects or being robust to external perturbations. More recently, goal driving navigation behaviors have been achieved in a relatively small environment on a real robot. So, inspired by the successful results, we propose to unify 3 main robotic systems for large-scale navigation in real environments. Our first system uses self-supervised visual odometry to encode the robot movement information. Here we show 2 recent works that address this problem, which have shown to outperform both deep learning-based models and also traditional geometry-based methods. Now, the key idea behind these 2 systems is the combination of both classical VO and deep learning for deep and optical flow estimation via self-supervision. The second component of our system deals with the problem of noisy GPS data. This model here has been able to outperform both fully and weakly supervised methods by learning self-enhanced image region similarities on a city-scale datasets with poor GPS data. And our third system is an interactive open framework called CityLearn, which enables the use of any driving dataset on top of a single learning environment for training navigation algorithms using reinforcement learning. So this is our full robotic systems for self-supervised navigation learning, where we train our agent using a single image sequence from where we obtain both motion states and visual observations in a self-supervised manner, and these visuomotor representations are then temporally integrated using this reinforcement learning policy network, which also requires goal destination and previous action signals. So here are some of our qualitative results on 2 large datasets, where we can see that our approach is capable of generalizing to extreme visual changes. Now, to analyze the influence of motion estimation precision, on the left we compare the results of the self-supervised network against a classical VO method, where the former achieves comparable results with the ground truth data. And on the right, we show how the motion estimation precision can affect the overall navigation success rate of our full system. Here we report our training curves on the KITTI dataset, where we also compare our full model in green against 2 different baselines in blue and orange. In this case, our full model required less training episodes compared to the vision-only system. We also provide some deployment statistics here, where our full model achieves up to 80% navigation success rate compared to 65% for the vision-only system. On the other hand, the agent using only motion information on the left seems to compete with our model, but its main limitation is that it doesn't incorporate visual data for distinguishing between environmental changes. On the Oxford dataset, we interestingly found that our full model can actually train faster than those vision and motion only methods, and here we show that our model is capable of generalize from day to night, where vision only navigation systems typically fail. So to conclude, we got 2 key messages for you, and thank you for your attention.